Thank you, Jurgen, to give me this talk on climate over the Himalaya. It gave me a time after COVID to relook of the past work, what I have done, which otherwise I kind of kept it. And it's good that it started in that way. So Himalaya, when we are talking in that sense, Himalaya is a very beautiful massive which is protruding out of the surface in the geological scale, and it has a very many manifestation from global to regional to local scale, and simultaneously it is kind of influencing very many societies. Of course, surrounding nations habitats are influenced. So, and very many good researches has been done by various people on the total water storage, elevation dependent warming, winter weather, controlling the El Nino and Indian summer monsoon. If you look at the its structure, geology people will tell it better than me. When the continent collided with each other, the origin of Himalaya started only 15 million years back. Indian summer monsoon started, right? Because it stopped the northward propagating air from Indian Ocean side, and hence the monsoon started. And by virtue of this striking over the Himalaya by this rain, you have a weathering, physical weathering started, and that's where how the sediment mountain of the Siwalik have grown up. The foothills of Himalaya is mostly the sediment mountain, not the tectonic mountain, where the higher Himalaya is the tectonic mountain. So it's a very beautiful, complex puzzle existing at the surface, and it's controlling various domain apart from meteorology and science and so on and so forth. It's have a very important biodiversity from an agriculture point of view, from society for domain, and I congratulate co-prepare team to have a genesis of three important questions out of this co-prepare team that they are trying to look in this present this thing. So if you look at the Himalayan region, if this what I am showing is I am just limiting my discourse today on the Indian Himalayan region, and you can see in a very short span it runs from 500 meters in the foothills of Himalayas to the higher Himalayas, and then Janskar range, and then Ladakh, and finally it arrives at Karakoram. And then we have kind of almost 4 or 5 ranges running parallelly together over these regions of the Himalayan in per se. Having said that, not only the topography or geology is a key issue here. Here is the very key issue is the heterogeneity of land use. Apart from the variable topography, land use change, land use cover interacts with the existing atmosphere in a very different manner, and by virtue of that there is a lot of control over the Himalayan region is happening. So most of discourse I am limiting today on the observation, and then with the some of the set of the model. There is a lot of observational uncertainty. If you look at the blue graph here, we see that it is different observation analysis mean I have picked up from Aphrodite, from GPCC and crew, and this is a precipitation I am seeing. Within the graded observational analysis, we find there are a lot of uncertainty within the observation. Of course, all of us know that there's a paucity of in situ observation, so I'm not going in the observation network at the moment. It's a altogether a different data observation point. So there is a lot of climatological uncertainty in the precipitation distribution. Distinct role of topography has been seen. Distinct role of valley is very nicely seen here. Distinct role of seasonality of the winter precipitation, summer precipitation, and very oftenly we forget the spring precipitation. We don't see it here. And coming to the precipitation distribution on the elevation, if you look at this graph here, we see that at the lower foothills of Himalayas, our spread of precipitation is very, very large if you look at the variability. But as we climb up, and then we see that in the higher Himalaya, your cluster is closer together in 4,000 and 5,000 meters. So they are clustered together. So distribution of precipitation is primarily, it says that there is a lot of orographic forcing and driver mechanism is working when it is coming to the precipitation forming mechanism over the Himalayas. So more interaction is happening on the foothills of Himalayas in forming precipitation mechanism, which is more complex. But as it climbs to the mid Himalayas and above, we find that precipitation forming mechanism is not very complex because of the existing temperature moisture feedback mechanism. Maybe I'll, if time permit, I'll touch upon that later, that moisture temperature feedback is very, very important. And if you look at the precipitation trend as we climb in the adjacent slide, if you look at here, we see that at the lower Himalayas, trend is gone negative in past 30, 40 years if you look at the grid distribution. But at higher Himalayas, if you go, the precipitation increasing more. There are likelihood that the energetics due to the increased temperature of the global warming is pushing the precipitation forming cycle or precipitation forming mechanism to the higher Himalayas, because there is a lot of available energy in the existing time. So we have seen that because of the increased temperature at the lower, so in lower Himalayas, we don't have that much kind of faster precipitation mechanism occurring in the recent decade. And as higher Himalaya it is going. Coming to the temperature side, if you look at the different season, winter, spring, monsoon, and pre-monsoon, the temperature is kind of also in this graded observation is not similar. They have very different distribution. Of course, higher Himalaya is the colder, whereas the lower Himalaya we see the warmer temperature. But what I want to highlight in this thematic graph overview is that within the observation, what we are using in our analysis, all the observation, whatever the synthetic method they are generated, whatever the statistical robustic method they are generated, they have very different distribution of precipitation over this region. And so is the elevation dependent changes in the precipitation has been seen. I will come to that. In valley in Himalaya, basically atmospheric dry adiabatic lap state doesn't work. So we have already proven it that we call it slope environment lap state, because when you are talking in valley, so valley floors interact with the atmospheric moisture and it doesn't let the atmosphere to be in the atmospheric layer. Codex is very popular. Experiment has been done. Now we are working for Codex Core. I think all of you must be working from Codex Core. Few work has been started, but because of COVID, I could not have a final result. So maybe sometime later we can discuss that. And in the essay experiment, we have picked up few of the available regional climate model. And based on these regional climate models, what we are trying to show that how best we can evaluate the and judge the mean cycle and precipitation along this. And then after having evaluated in the present monsoon precipitation, we can go into the future. And also we have done for winter. If you look at the spatial distribution of this JJAS mean, that is the most forming precipitation season in India for most region. You look at this JJS mean, which most of the model in the foothill are drier. This shows the bias. So in the foothill model environment is dry, but as it climbs up in the higher Himalayas, model it produces more precipitation over the higher Himalayas. So it distinctly shows that as the model orography is interacting with the precipitation forming mechanism, or its representation is the precipitation forming mechanism over the Himalayan region, it's very critically underestimated the precipitation in the foothill of Himalayas as the air parcel started climbing up. Because we must also here briefly try to understand that Indian summer monsoon is 850 hectopascal flow, which is coming from the southern latitudes of Indian Ocean or Bay of Bengal. I'm not going there. And it hits first the foothill of Himalayas, and then it climbs up. And if you look at this altitudinal distribution of this, it shows very distinctly different distribution in all the models. Of course, higher elevation, if you look at this graph of 9 models and their ensemble, no, it's 11 models and their ensemble, we see that at least model has a capability to capture precipitation distribution in the higher Himalayas. If you look at the elevation dependent graph, and higher Himalayas, the clustering of the distribution is closed as seen in the observation, which is at the left hand side. But if you look at the foothill of Himalayas, most of the model are unable to capture the precipitation distribution or its intensity. So it's not that spread. So what we concluded from these most of the model, and we recommended for the climate modeling community that how at the foothill of Himalayas, your precipitation forming mechanism within the model framework is kind of not capturing most of the time. And also with some few cases, how the uncertainty we have tried to improve upon for downscaling, what my colleague Rupam has stated, that how we can improve on this, because with such precipitation and temperature fields, it's a very, I would rather put it in a way, it will be very brave to use it for glaciological and hydrological purpose. Otherwise, it's very deceptive. So what we try to do, if you look at this graph, we have taken this all 11 model, and based on this 11 model, we compared the various statistics over this region, over Himalayan region, that what best model could be. And we found that ICHC, Earth SMHI RCA4 comes out with the best performing model. It comes to the very closest to the observation comparatively, and it's best for using for the downscaling. And matter of fact, if you are trying to look at the bias correction or any kind of a statistical method on it. So if you have this kind of distribution here, we can distinctly see that what model is deviating from plus minus to standard deviation and something like that. Their frequency distribution also, when we saw that there is a problem in the lower intensity event, but higher elevation, it's very difficult to capture. In case of scatter plot, if you see that overall distribution over all the domain independent of elevation, if I put it like that, we find that lower intensity event is getting captured, but higher intensity event are not getting captured, like cloud burst and flood and all those leading to flash floods. Those events in the model framework is deviating from observations, whereas this scatter plots distinctly show us that there's this distribution at the less amount of precipitation per day, millimeter per day, is very well captured, and lower precipitation area then matches well. So based on this precipitation uncertainty, we found that with some interim conclusion, if I have noted it here, that performance is very capturing various aspects of precipitation climatology over space and time. But generally, most of the experiments show consistently a wet bias over the higher Himalaya and low bias even in the ensemble. When we do the ensemble of 11 member, we find that this is the case. And then uncertainty suppression or reduction of uncertainty can only be done based on some bias correction, because now we definitely have few more increased in situ observation, which we have shown by other methods of bias correction, all the bias correction method in separate work. I am not bringing that here. We saw that how these uncertainty in any of the model can be reduced to the minimal based on the various bias correction methods. And then this corrected data can be used for hydrological or glaciological or many other purposes, which is possible here. In case of temperature, when we saw that, then higher Himalaya are much colder, they become much colder, and lower Himalaya, we say they are comparatively colder, but not that much colder. So lower Himalaya is still in model environment is kind of a warmer, and this temperature in the model becomes very smart in the sense that when we are talking of moisture temperature feedback mechanism to over the Himalayan region based on the slope environmental lapse rate, based on how this flow of vorticity when it is climbing the windward side of the front of the Himalayan southern front, how it happens, and when it crosses the higher Himalayas, then temperature is decreasing. So it leads to that forming of the precipitation energetics, which is kind of hampering that. At lower Himalaya, temperature is such in the model, it doesn't let the natural environment or natural precipitation to be reflected in the model physics. So that is the big problem of the model physics, on which there is a need to be work, or we are working that how to improve this for, and we are planning we have proposed a Codex Himalaya in which you at a very shorter domain, we are planning to improve upon these kind of features. And if you look at this various model distribution on this graph, of course, the cold bias is there. In this cold bias, we saw that March of the monthly annual March of the cold bias is very, very similar in all the model, but it is colder. But one thing, when you see over this distribution of curve, we distinctly find here that they match exact distribution as far as their March is concerned, but they are colder than the observation. Black curve is observation. And also when we have their distribution with the model and all, we find that, I'm sorry that this is a very smaller written slide, my apologies for that. We found that when we look at the Gaussian distribution with the corresponding observation, sometimes we found that either they are skewed to left or right, or sometimes their mean is suppressed, And these statistics tell us in the way for correction of downscaling model or bias correction and so on and so forth, then how best we can employ these methods for controlling these. So sometimes if we are looking for only seasonal control, then we are more interested to look into the mean only. But sometimes if we are looking for the colder or warmer number of days in the model, then we are looking for the extremes of this Gaussian distribution in the model, and hence we need to correct those data according to our scientific objective, if we are talking of seasonal mean or if we are talking for the extremes. So that's what we try to work on that. And then we also have looked at how the altitudinal distribution bias in model shows intensification in most of the cold bias. That is the major problem in this Himalayan region. And let me put it other way also, that this kind of biases primarily is how much observation over the Himalaya is going to the observational analysis also, because most of the observational analysis also inculcate these observation, in situ observation or satellite information. So Himalaya is works as a kind of a void of the observation, and most of the synthetic data which is generated by this observation analysis is kind of a, I should not say interpolation, but it's kind of a producing a synthetic data over the Himalayan region with whom we are comparing the model results. So that factor also remains there, that how good the observational analysis available with us. So that could be any reason. If anybody of you wanted to generate a grid data over Himalaya itself, that will be very good exercise under the co-prepare based on the available observation. If only one gridded data can be applied. Some people from Europe has done, I think Emergil group has done, or GHCN group has generated that data which we are using, and many of us are using. Coming to the climate change, if you look, it's a very interestingly, we found that if you look at the first graph here, in near future, it's a 2040, 2020 to 2049 we have seen, and we found that Indian summer monsoon is no more going towards eastern side, northeast region, which is the highest precipitation receiving stations, and that could be one of the reasons that the maximum precipitation station has moved from Darjeeling to Mosinram. Mosinram now from last few years is the highest recording precipitation during monsoon time. So most of the model, whatever they are showing in the near future until 2049, they saw that Indian summer monsoon most probably will not yield much precipitation on the eastern Himalayas, but will likely to have more precipitation in central and eastern Himalayas, with the uncertainty already which I discussed in previous cases. So if it happens, then is there likelihood of a reduction of the surface availability of total water storage in the northeast region, and more in the western Himalayan region or central Himalayan region is likely. Of course, some model shows in differently, but that remains a question. And then separately, we also did a research on the Indian summer monsoon, and we found that Indian summer monsoon is kind, if you have a Indian map in your mind, it shows that Indian summer monsoon march is shifting towards westward. That is the few cases of the flooding in Gujarat, Banaskantha, Rajasthan in the monsoonal flood time has been reported. An ensemble of the long-term ensemble of this looks like this, where the precipitation is increasing over the Himalayan region. If I'm averaging, of course, this average over the Himalayan region will be kind of somewhere it is imbalancing in the 8-member ensemble member. In case of elevation dependent changes and percentage strain in different RCPs, 2.6, 4.5, and 8.5 during winter time. First panel is for winter, lower panel is for monsoonal time. We find that there is a lot of variability is going to be there in the winter precipitation, Indian winter monsoon precipitation from present. And whereas Indian summer monsoon, we find that in the 2.6 RCP, it's likely to be the less variable. We have kind of a more precipitation at the lower elevation also, if you are looking from the trend. Whereas in case of higher Himalayas, it is likely to be increasing. Maybe the higher Himalaya is likely to be getting drier. I am coming to those slides. So if it is getting drier, more amount of moisture is needed for getting its saturation. So lower elevation shows increased variability in future, higher precipitation, and the feature gets more prominent as we go to the more pessimistic RCP scenario 8.5, and this leads to the uncertainty in the higher Himalayas also. In case of seasonal mean temperature, well, all of us know that there is likely increase of temperature. We have done initial analysis of 1.5 specific warming label, 2.5 and 2.4 also, but we are not showing it here at the moment. One distinctly clear, we have seen that if you look JJS overview graph, there is a dampening of the variability. This dampening is primarily because of not any other reason, but in the monsoonal month, we have a lot of moisture available in the free atmosphere. So what it does, this moisture holds the temperature not to be freely varying as in case of winter and in case of kind of a summer, in case of pre-monsoon or post-monsoon. So pre-monsoon, post-monsoon comparatively are less drier than monsoonal time, and hence temperature variable is more free to oscillate in their capacity, whereas in winter, summer monsoon time, it holds it very tightly. So there is a dampening of temperature variability is seen in JJAS. And based on two of the model, if you look at here, the ensemble, higher Himalaya, we have increase of more temperature. Higher elevation, higher elevation, we find most of the temperature increasing in most of the month than lower elevations. But in case of again monsoon, because the availability of moisture, it is kind of restricted, it is kind of not going haywire as seen in the post monsoon time. So based on this consistently increasing trend is noticed in all the season in 8.5, what results I am showing here, and pronounced winter time warming is projected in coming time. So if Himalaya is getting warmer, of course it will have very many ramifications on the water impact and so on and so forth, the snow maybe, so it needs to be seen in coming time. And then winter warming elevation dependency mechanism, we have looked at that how the winter warming is kind of having more in the higher elevation. If you look at the trend of mean temperature, but here we found that in the mid elevation in particular, which in case of you look at the mid elevation is the region which acts as a threshold when we are trying or to understand the Himalayan moisture and temperature distribution. In case of mid elevation, we find the characteristic above the mid elevation is entirely different than below mid elevation, and that mid elevation roughly we find it is somewhere in between 3000 meter and 3500 meters in Himalaya. That this belt beyond and below this belt, we find that there are distinctly different regions of controlling for the elevation dependency of warming as far as temperature is concerned. It could also be possible from the cloud forming processes, because LCL, lifting condensation level over the Himalayan region, sinks a little bit. So that could be a reason that it is happening in that way. So we try to explain one proposition with the skin temperature. If you look at this A, B, C, D graph, this is the skin temperature averaged over 35 years over the Ladakh region, giving just a kind of a flip for anomaly, which is explained in the model Karakoram anomaly people have talked about. And we try to look into that, how could Karakoram anomaly can be explained based on the physical processes linked to the snow temperature and surface snow amount and associated radiation fields. So we found that this is the temperature trends are negative over the Karakoram and Ladakh region, and simultaneously trend of snow has been increasing. So when temperature is decreasing, snow trend is increasing from last 35 years, which leads to the increased upwelling short wave radiation and upwelling long wave radiation. So what I mean to conclude in a kind of a snow albedo feedback manner, that in this region in particular, the energy is not getting retained over the Karakoram region by virtue of the various physical processes, and most of the energy which otherwise could have been utilized in melting the glacier or snow mass. So I'm not talking on the glacier dynamics because I am not glacier person. So I'm only giving a conjecture of the associated atmospheric forcing to the snow or glacier mass over the Karakoram and Ladakh region. And so that is the one which we are trying to hypothesize, that through the increased albedo, something like that, it will happen. And then over Karakoram, we went extensively. If you look and we try to compare the adjacent Ladakh region and Karakoram region, they are adjacent. In principle, they should not have very much difference in their regional climate, but then we found that Ladakh and Karakoram has a lot of difference in their regional climate. In particular, rather I would say microclimate in particular, by virtue of their positioning away from the incoming winter monsoon or western disturbances, because they are kind of uh, a shadow zone of the precipitation. So you have a cold desert in Ladakh. Simultaneously, you have a less amount of precipitation over Karakoram, except the western higher side, which interacts with the incoming western disturbance. And what we found over this region, that annual mean precipitation climatology over the larger Himalayan region shows that Ladakh and Karakoram has a very distinctly different regional climate. If you are trying to talk of the precipitation, that's very peculiar for me to understand, because both of these regions are primarily getting fed by the winter weather, and summer monsoon precipitation do reach there, but that is not at that level, because it's a very far, and then you have to cross various Himalayas. So most of the this thing, and simultaneously, when in the lower panel I am showing the precipitation temperature distribution, if limiting to the Karakoram and Ladakh region only, we find that near surface temperature anomaly on JJS monsoon and winter time is entirely different. If you compare Ladakh, I have tried to put Ladakh and Karakoram in this thing. So there is a lot of difference. And when we are talking of the trends in this winter and summertime season for Karakoram and cold region, this figure shows that how the changes in and trends in Karakoram and cold arid region during monsoon and summertime is happening. And we find all the time Ladakh is kind of a warmer than the Karakoram. So Ladakh remains warmer than the Karakoram, and that is one of the reasons that what we are trying to propose here, that most of the elevation dependency of temperature and Karakoram, what we are finding over the Ladakh region, is primarily because that higher elevation of Karakoram region is very close to the atmospheric level of lifting condensation level. So whatever moisture is coming over this region from any source, it is getting dumped over this region faster, because all the moisture, by virtue of being very closer to lifting condensation level, is completely condensed, which is not the case over Ladakh. Based on this precipitation and temperature patterns, we found that this is the range. And in case of Ladakh in particular, if you find that in lower elevation, we find that this is the case. And here in the heredity pattern affirms the Karakoram anomaly. If you look at this heredity climatology and heredity trend in per se, that Karakoram has more heredity, getting more arid as compared to Ladakh. The rate of trend in the second figure you distinctly will see blue color shows that heredity trend from last 35 years over Karakoram. It shows that affirmation of Karakoram. So it is getting more amount of precipitation. If you are looking, it's going to more humid side as compared to the Ladakh side, which is going to the arid side. So Karakoram is becoming more and more arid comparatively, if we are talking on the trend in last 35 years and based on the aridity index primarily. And here the proposition which I was discussing, that how the lifting condensation level patterns affirms Karakoram anomaly. So LCL determines that how much of the moisture is getting dumped over the region. Primarily, that's what we are trying to look at here, that LCL is making that most of the moisture which is available in any form is kind of getting frozen. And these trends in lifting condensation level height during summer shows it's lowering of the Karakoram. So LCL trends in last 30 years, we found that it is decreasing over the Karakoram region. It means that it is coming much closer to the surface. And in winter, there is a more lowering, particularly in winter time, a lowering is higher. If you look at the last line graph, the lifting condensation level in winter, because of the colder temperature, your atmosphere is more stable as compared to Ladakh. So this all proposition which I am talking is primarily based on the comparison between Ladakh and Karakoram. So we kind to see that there is a kind of exchanges of stability are happening or not. And then this increased summer cloudiness is associated mainly the monsoonal moisture, summer moisture, which is going over these regions in some few of the years. It says that warming is this clouding primarily in the summertime is cooling the surface to by stopping the incoming solar radiation. And that's what is the very famous and landmark paper of Habitat of 2005, which says that so warming is reduced by virtue of the decreased LCL leading to form more clouding. More clouding means more cooling by stopping of the incoming solar radiation over the Karakoram anomaly. Secondly, I am working very extensively over Upper Indus Basin. We are having a kind of a collaborative Indian chapters, Pakistan chapter, China and Afghanistan chapter. So we are working on various aspects of Indus Basin, primarily climate, even gender, socio-economic issues, of course, cryosphere, and various. So Indus Basin, because it's a very important in various aspects apart from geopolitics. I'm not going in the geopolitics of the Indus Basin. So this is limited to the how this cryosphere in the Indus Basin and climate change will happen in present and future, and how could it benefit the society who are living there, in the sense of that what are the gray areas by virtue of its very peculiar geographical sub-region of the larger Indian HKH Himalayas. And that shows that from last 120 years, 131 years, that unanimous increase in temperature. That's very key message from this finding, that there is a increased temperature, and that what's in all kind of model, in all kind of scenarios, you have that increased temperatures happening over the Upper Indus Basin, and this will lead to the more melting of the snow mass or glacier mass. We don't know. Maybe in future it's going to happen. In separate study, we found that there is an increase of the hydrological runoff because of this increased temperature. And this RCP warming trend are also showing that in higher RCP we have more increased warming over these regions. So this is very peculiar and this is very challenging, particularly by virtue of increased precipitation. If these models are assumed to be correct up to certain degree or certain extent, if they are giving these kind of signatures, so we have to be very cautious for this particular region, because this is very sensitive to climate and all other point of view also. And by trend of precipitation, if you look, that lower riparian of Indus Basin is likely to get drier. So as I told in previous slides, that Indian summer monsoon in particular is playing a very different dynamical role. I will not discuss here Indian summer monsoon dynamics, but the shifting of the Indian summer monsoon towards northwest side, it is intruding more into the Indian Himalayas, in the Indian side of upper riparian of Indus Basin. So we have more likelihood is that we will have more amount of precipitation in next 120 years over the higher Himalayas, but it is not encroaching in the lower riparian side. So there is more drying is going to happen in the lower riparian of Indus Basin. So rest of the basin, which is in lower side, is having the declining in the precipitation. Yes, there is likelihood that the topography of the Upper Indus Basin is kind of playing more dynamical role for initiating the precipitation formation or precipitation mechanism, which is not the case in the lower riparian, which is more flat in that sense. So that's what is another very unique finding from temperature and precipitation, both if we are considering in that way. And if we look at like that, and if we take a very simple water storage method of only evaporation and runoff, then we find that in different season, if you look at different season, that JJS shows that in the winter time you have more precipitation. Of course, it is primarily because of climatologically. If you look, it's a winter time, we have more precipitation due to the western disturbance, we call it in Indian context, or Indian winter monsoon also we call it. But in case of the water storage, if you look in JJS time, there's a decrease in the climatological water storage we find. And if this happens, this trend shows that in case of upper riparian of Indus Basin, we are probably will have a kind of more increase of the water storage likely is there, but that is not very distinctly clear that if water storage is balanced between the precipitation minus evaporation and runoff. If that is the balance we are taking, precipitation minus evaporation and runoff, in such case, thus we conclude that JJAS, which is the main precipitation forming and yielding season, we find that upper riparian of Indus River Basin, which will be more usable for downstream. So we have to be very kind of more pragmatic in formulating any project and plan in the upper riparian of Indus Basin, which do not affect the society or habitat in the lower riparian Indus Basin. Over the climate change in the Kashmir Valley in particularly is a very interesting. If you look at this topographical figure of the Kashmir Valley, it doesn't follow the elevation dependent warming which I discussed earlier. In earlier figure, we said that the higher elevations have more warming rate than the lower elevation. But in this case, in this particular valley, which is part of the Himalaya, we find it's very different. Higher elevations warming rate is less and valley is warming more. And then we try to look at that, why this valley, which is in the green color, is kind of having more precipitation based on the 4-5 stations data all across this valley floor and the ridge top. We found that lower rate of increase in elevated mountain region is fine, which is not the case in Himalaya. As I said higher rate of increase in the higher Himalayas. Primarily what happens over this valley region, the population uses a lot of fuel which gets trapped within the valley, because valley is not allowing it to interact with the above atmospheric flow. So this is kind of a trap within the valley. Hence the regional microclimate of this valley is entirely different than the rest of the Himalaya. So this kind of situation in the valley floor in particular shows that the warming rate of Kashmir Valley and rest of the Himalaya is distinct, contrastingly different over this region. And we tried to publish this also, and it has already been done. And in case of precipitation, if we go from based on last available data, because we have chosen this valley for a specific case study, and one of the PhD student from Kashmir University, he has done a very wonderful job in this, that how the precipitation trend in different topographic zone of the Kashmir Valley, Karevas, and so forth, foothill, plains, mountains, and Karevas, and how these different plains of the Himalaya within the valley is kind of giving in particularly precipitation change because of the Jhelum flooding or water supply to the society over these regions. So this is what Satluj River Basin, which is in the central Himalaya, it doesn't change much. We found very surprisingly within the Himalaya, whole Himalayas, your precipitation and temperature trend, when we cut at a smaller basin scale, we have not seen there is a much change in the precipitation in the right hand side. In the left-hand side, yes, definitely we found that there is a kind of increase of temperature, but that increase of temperature is not very rapid as in other parts of the Himalaya. And in comparison with the India Meteorological Observation, in Upper Ganga basin, which is a kind of a more complex in the sense that it is at the cusp of winter and summer monsoon both. So both the monsoons arrive there, and it has a very different kind of a land use, land cover. It has a rock, it has a vegetation, it has a clean ice, debris cover, even glacier also. In this case, what we found over this, that future climatic changes impact is comparatively less than the Western Himalayas or the Eastern Himalayas. So the central Himalayan part of this upper Ganga basin, only limited to Upper Ganga basin, we find that projection shows that there is not much changes has been seen in the model framework, maybe because of the representation of both the monsoon from summertime and winter time kind of having a different dynamical role to play. And hence, at least in snow melt and precipitation, what we saw based on these two RCP and compared with the historical time, we find there's not much change in the trend also. So the conclusion from the overall conclusion from the talk is that temperature are projected to increase in terms of variability and magnitude all along the Indian Himalayan region per se. In the higher Himalaya, the warming rate is more. In the lower Himalaya, warming rate is comparatively less. Regional responses are very, very different. So we cannot kind of make a composite regional response here. So regional responses are varying in terms of precipitation, in terms of temperature. However, in the Western Himalaya and Ladakh and Karakoram side, the temperature have more pronounced effect than the precipitation. We have to see more interactive mechanism of temperature and precipitation. So we are taking some observation from last 2-3 years over the Himalayan region and in the Central Himalayan region. Uncertainty is I will not go in detail because all of you are using models, so all of you definitely know that modeling framework people are trying to improve again and again with the best experimental setups, best experimental styles, best experimental methods to improve on the model. Precipitation projected to intensify in lower Himalayas, as we have seen that a higher Himalaya will become drier and drier, and we are trying to give a hypothesis based on snow model feedback based on the regional climate model. Yes, we have no, since we don't have any observation, so we kind of providing a hypothesis based on the model physics only, but based on observation we have yet to see that what happens over the reason for this feedback mechanism over the Himalaya. So maybe these are the few way ahead I thought of. I had a very good discussion with Professor Rupam, and these are just suggestion, need not necessarily to be included in the study. Of course, impact and adaptation, they are doing it, and we have to see how reliable scenarios, if we can choose certain region or certain basin, improvement on the observation. That is all time along comment from most of the Himalayan researcher, that how can we can improve on the observation to understand the topographical complexities, its implication, heterogeneity over this, land use changes, because now some of the Indian states are telling that forest is increasing, so the land use, land cover is changing. And then other observation, we find that there is a kind of intervention occurring in the pine species with oak species. If this interaction of two plant species are occurring, is there likelihood of the evapotranspiration will change? So these are the few questions maybe we need to, of course, I think Sumit Sen is involved here. So he is a partner in that project with us. So in view of this, these are the few comments. And I thank you, Professor Jurgen, Ankit, and Professor Rupam for giving me this opportunity. Thank you very much.